Hello, everyone. Welcome to Zoom session on Tuesday, June 23rd. And I'm going to continue with chapter 3 lecture and hope those people that are not here will be able to watch this so that, and also those people that are here, they can go back and watch this video. And if I'm not able to post it on Canvas, I'll post it on YouTube, and then I'll post a link on Canvas. Okay, all right. So in this, the second part of chapter 3 talks about three-dimensional force system. The first part that I've already lectured on was two-dimensional force system. Was not that complicated. Okay, equilibriums of particle, and we talked about the summation of forces in x, y direction. We set it to 0. Now on this topic here, we're going to have Z also, summation of forces along the Z axis is set to 0. Okay. If you go to maybe this here, this is the scalar equation for equation of equilibrium, a scalar, and this is a Cartesian format. Okay. If you look at the three-dimensional equilibrium or equilibrium, okay, let me see if I have that. Remember, the information or the knowledge that you acquired from chapter 2 is going to come back and help you in this chapter, especially position vector, unit vector, force vector. If a force given on 3D, it's on X, Y, Z plane, and you need to find a position vector, unit vector, and force vector. But if you see a force on a YZ plane, then you don't need to worry about that. If the coordinate direction angles is given for that force, then you just multiply by cosine alpha, that magnitude given, you multiply by cosine alpha, cosine beta, cosine gamma, and there we go, you can convert the magnitude of the force given to Cartesian vector form, all right, which is this form here, all right? So we're gonna continue and example, okay? Let's just, this example will clarify what I just said, okay? We'll just reinforce it. All right, so we have four forces as shown. Force number 5 required to keep, we need to know, because we don't know the magnitude or the component of the magnitude along the x, y, and z, which we call it the force vector in ijk. We need to find that so that we can keep the particle O in equilibrium. So say, think of this as an O. Okay, great. We go one at a time, okay? We look at the force number 1. We know that this is a position in a YZ plane. Force number 2 is along the negative x-axis. Force number 4, it's located in XYZ plane. So we need to find the position vector, unit vector, and force vector, convert the 200 to what? To Cartesian vector form. Similarly, you say force number 5 in Cartesian vector form, you say fxi plus f5xi, f5yj, and f5zk. So then when you add all the forces, you see that in that number of equations, you have number of unknown, you solve for the force number 5 along the x, y, and z axis. Okay, we do this. It says force number 5 is fxi, but actually it's a f5, but that you understand what's going on, okay? So fxi belongs to number 5, fyj, fzk. Write f1, f2, f3, f4, f5 in Cartesian vector form, apply the 3 equilibrium equation to solve the 3 unknowns, and there we go, okay? And there we go here. So force number 1, it's step by step, 300 times 4/5, okay? Because we don't, this force number 1 is located in what? In a plane called YZ plane, okay? YZ plane. So there is 0I plus 240J plus 180K. That's the force number 1 converted to Cartesian vector form. 300 times 3/5. Okay, you know that, okay? Because prerequisite for this chapter is chapter 2, and you should be really knowledgeable on chapter 2 by now. So force number 2 is along the negative x-axis, so it's a minus 600I. And then force number 3 is along the negative z-axis, so that's a minus 900K. And this is the notation for the what? For the vector, okay, symbol. We call it braces, okay, braces. All right. So that is force number 3. Force number 4, there we go, chapter 2. Magnitude of the force times the unit vector. What is the unit vector? Position vector over its magnitude. So you know what to do. You know the coordinate of O, which is 0, 0, 0. And then coordinate for A, for this point here, we have 3, 3, -4, and 6. So 3, -4, and 6. So this is 3, -4, and 6 is right there. Okay. So 3I minus, even if you go head minus the tail, since the tail is 0, so you stay the same. The numbers stays the same as this coordinate that we have in here, okay, at that point. So divided by magnitude, you know what the magnitude is, and then you come up with this number for x component, this number for y component, this number for z component, all right. Then we are going to, let me see if I can move this all the way up so that there is no interferences with the, okay, perfect. So then force number 5 is Fxi minus Fij plus Fzk. So we have total of 5 forces here, 5 forces. It could be on the exam, okay? You can see the same question on the exam, the different numbers. Okay, so then you're gonna collect all the i's, collect all the j's, collect all the k, and set it to 0 because it is equilibrium. So summation of forces in x direction, that means we pick from all the 5 forces, we're gonna find, we're gonna collect 76.8, because 76.8 is, it's force number, let me see, this is summation of forces in x, which is minus 600, 76.8 is right here. They should have just gone like this, minus 600 plus 76.8 and plus fx, f sub x. So those are the 3 i's, okay, the 3 i's. This force number 1 doesn't have I, okay, and force number 3 doesn't have I. Okay, great. So you collect all the i's and you write it here, and fx is this number. You collect all the j's and you solve for f sub 1. You collect all the k's, you solve for fc. This was the easy problem because you didn't have to solve systems of equation. All right, so that makes sense. All right, so then we go to next, and then force number 5, and therefore is it's a 523 because we already found the fx, because we said that force number 5 is fxi minus fyj plus fz. So now that we have fx, fy, fz, we plug it into the, you know, the Cartesian vector form for the force number 5, and there we go. That's a force number. If they ask you to find the magnitude, you take the square root of these numbers and square each component, and you get the magnitude of force number 5. Okay. So using this force vector, you can determine the force's magnitude and coordinate direction angle as needed, but not in this example. Okay. Not in this example. Maybe example number 2. Okay. Put your seatbelt on. So we have a 600 Newton load is supported by 3 chords. Okay, we have chord AB, chord AC, chord AD. Chord AC is along the negative x-axis. Chord AB is on XY plane. This is the X and then Y plane. And then chord number D, or chord D, AD, is located on XYZ plane. So you have to find the force vector. Okay. All right. So a 600 Newton load, we have a 600 Newton load along the z-axis in the negative direction. So this system is supported by 3 chords with the geometry as shown. We want to find the tension in chords AB, AC, and AD, the way it's shown. Okay, so there we go. Tension in chords AB, AC, AD. So we draw the free body diagram, represent each force in Cartesian, apply the equation of equilibrium. That's a standard, okay? That's a standard. Okay, we go to here, and that's a free body diagram, and everything is ready to go. and we can find the force AB, which is FB, the magnitude, times the sine, because that's parallel to the x-axis, sine of 30 degree I, plus cosine of 30 degree J. So there is no K, right? No K. So then this is simplified as such, okay? Make sure that you show your work in this fashion, okay, this way. And then force C is minus FC I, okay? So that's what we have, whatever the magnitude is, I. Okay, next. We go to FD, we have to find the position vector divided by its magnitude, and then we can just convert that to Cartesian vector form, which is written like this, okay, IJK. So now that we have the information about the force B and C and D, now we can combine it, all the I on the, all the J, all the K. So IJK, now equate the respective IJK components to 0. All the forces in X, we have 0.5 FB minus FC plus 3.33 FD. And then collect all the J, 0.866 FB minus 0.667 FD. And then Z is, you have only one unknown. You solve for this FD. We plug it into equation number 2. We solve for FB. And now that we know FD and FB, we plug it into equation number 1 and we solve for FC. That's easy. So far, not that much work, okay? Not that much work. All right, so so that is really straightforward, okay? Nothing really challenging in here. As long as, yes, go ahead.
Sorry. So when you were getting the vectors for I noticed that you only did the unit vector for FD.
Yeah, the unit, because the D is located in XYZ plane based on given the coordinate, which is 1 and then -2 and then 2, I believe, yeah, and -1, -2 and 2. So from this point, you go straight up to get 2 meters. So you get 1 meters along the x-axis, -2 meters along the y-axis, and 2 meters along the z-axis. So
yeah, but you did it for FD, so you don't have to do that for FB, or you?
My friend Franco, just watch. FB is located in XY plane. Since it's located in XY plane, we don't need to find the position vectors and unit vectors, because you see that here, right here.
Yeah, I understand now. Thank you.
Okay, all right. So first you have to observe to see if the force is given on an XYZ plane or in XY plane or in YZ plane. So you can just have to, then after you observe it and you knew what to do, you tackle the problem, you write it down as such, because the force D is located in a space and we don't know where the location is of that. So we have to use the position vector, which is this here, divided by its magnitude. And from chapter 2, we have learned that if we know the unit vector, which is the ratio of position vector and the magnitude of the position vector multiplied by the magnitude of the force, we can write the force in Cartesian vector form. Make sure, if someone is rusty or doesn't understand, make sure you learn chapter 2 first about the position vector and unit vector, force vector. I've repeated that many times, okay, many times. All right, this is a calculus also. Okay, so we go here and we solve for all those forces. Since it is positive, it is assumed in tension. Since we have already assumed that these are all tension and the result came up to be positive, that will confirm that in actuality, these forces are in tension, okay? So since it is positive, it's assumed, the tension confirmed, okay? And that is what we have in here. At the end of this lecture, I'm going to bring another, I'm going to stop this share here and go and share another example. I'd like to cover this problem here, okay? So it has a spring attached to it, okay? A spring, all right. So now we have a problem it says determine the tension in each cord used to support the 100-kilogram crate as shown. And we have in one of the cord, we call it a spring. So instead of cord, we have a spring with a stiffness of 1.5 kilonewton per meters. And then for, if you look at the cord D or AD, is located in XY Z plane, okay? X, oops, sorry about that. X, this is parallel to the X, parallel to the Y, parallel to the Z. So we need to find the position vector, for unit vector, and force vector. So, but chord, let me see, chord number C, AC, since we know the coordinate direction angle, the orientation of this chord, it's been established by coordinate direction angles. Which angles? Alpha, beta, gamma. Alpha is under 20 degrees. Beta, that makes between the y-axis and the vector, is 135 degrees. And then the angle that makes between z-axis and the vector, we call it gamma, 60 degrees. Okay. Now that we are, analyzing the picture to see what's given to us, and we know that the spring is located along the positive x-axis. So the force of the spring is equivalent to the tension on this here, we call it TAB, and this is TAC, this is TAB, or F if you want to use FAB, that means the spring force, and then FAC, and then FAD, doesn't matter. Make sure that you convert the mass for the crate, which is 100 kilogram, to Newton, okay, by multiplying by 9.81. The force in each of the cords can be determined by investigating the equilibrium of point A, So we want to maintain the equilibrium because this is a rigid bodies, no motion. So we want to know what will be the tension in each so that there will be, this structure will be in equilibrium, okay? So free-body diagram, and then each force on the free-body diagram is first expressed in Cartesian vector form. And then you know that the coordinate of the D is -1, 2, and 2, correct? -1. Everybody is comfortable with just walking from the origin. If you walk from the origin along the x-axis is -1, negative x. And then along the y-axis, +2. And then along the z-axis, or parallel to the z, is 2 meters, which is positive. Okay. For FD only, okay? That was the question, saying that why not the other one? Because the other one has their own characteristics, the other forces. This guy has a characteristic of a magnitude of the force, and the unit vector, that is, if you multiply, you get the Cartesian vector form, okay? I really don't know how else I could explain it, what other way I could explain this. That's a very simple language of mathematics, okay? All right, so there we go. So now that we have analyzed the structure, we can say force B, which is this one here, which is AB, and that is a force, spring force. Okay? Oh, spring force. Okay, let me go back here. So we have summation of all the forces. Oops, let me see, where did it go? Let me go back to, oops. I think I lost track of where I was. Okay. All right, so FBI, okay, Federal Bureau of Investigation, FBI. So FB is we call it a spring force along the x-axis. That's why we call it I. It's only one dimension, I. FC, we have 3 components, and because of the coordinate direction angle, so we have FC cosine of 120 cosine alpha plus FC cosine beta plus FC cosine gamma. And you have this. Force D, you have to find the position vector divided by its magnitude, multiplied by the magnitude of the force. Now you have the FD equals to these 3 terms. These 3 terms in Cartesian vector form, which they really should put it on the braces. And then the author of this book got lazy and they did not place it on the braces, which they just, that's not good. But here they did a good job. It says the weight is -981 K. That's fine. That's the Cartesian vector form. And all they have to do is add the braces in here, add the braces here, add the braces right there. Then the language is complete. Otherwise, it's not. Okay, so I'm just trying to clarify. Okay, all right. So then you say summation of all the forces is set to 0 for equilibrium, and then you combine all that and make sure that you then collect, okay, when you just substitute all that, you collect all the i's, collect all the j's and k. So we have this equation, one equation, second equation, third equation, this equation has 2 unknowns, this equation has 3 unknowns, this equation has 2 unknowns. There we go. This is the good example of you're going to run into algebra solving systems of equation, 3 equations with 3 unknowns. You learn, you know that you have taken 100 units of math, you should know how to solve that. Okay, all right, so this is where algebra comes to the picture. So you can use your calculators as long as you just lay out the equation and then the work to show how the substitution or matrices, using matrices, you apply those to be able to get these answers. I don't need to see those work. All I wanted to see is equation 1, equation 2, equation 3. Therefore, I use my calculators, graphing calculators, which the calculus people in your math class, it was illegal. They said you are not supposed to use your graphing calculators. Everything has to be done manually, but in engineering world, we can say use your technology, okay? All right, so no problem. I'm done, okay? This is done, and I'm going to review for chapter 2 and 3 tomorrow, and make sure that you understand the language of quizzes and exams, because quiz that I gave you, it's good. It's clarified a bunch of stuff that if there you made some mistakes, you say, I'm not going to make the same mistakes on the exam.